The screen sharing is, yeah, just a second. You're able to, I hope, see my screen now.
No, sir, it's not.
Still not see if it is getting shared now.
Yes, sir, it's visible.
Okay, all right. So, well, good morning, everyone, and I would like to quickly walk you all through because I realize there is a limited time for me to explain things. So what I want is I want to provide a very quick overview of what is Industry 4.0 and industrial AI and smart manufacturing. So let me just quickly walk you through and get you a sense of, as you know, Industry 4.0. Industry 4.0 is not a new concept anymore. It's been there for a couple of decades plus, and this looks at the revolution in industrial manufacturing practices. And it has a history to it. It started with Industrial Revolution 1, followed by Industrial Revolution 2, then 3, and now the fourth. And what you really see is that industrial revolutions are literally a shift in the way we do manufacturing. And this is something which has been seen from various past events. So the first industrial revolution was when we started using the steam engine, and that was something, steam power was driving the whole aspect. And then the second industrial revolution came when we had the electricity and the mass production using assembly line, which came in. And then the third industrial revolution came when there was automation, computers, electronics, sensors, they were all brought in. And that's how we have these CNC machines and all robotics, manufacturing systems and all those things. And that is the third industrial revolution, which has been there for a very, very long time, over 50 plus years, 60 years actually. So now the question is that if the third revolution already had automation, computers, electronics, sensors, robotics, what is new in the fourth industrial revolution? What really is the fourth industrial revolution then? And the answer is that all of those things are, of course, there, but the key differentiator in fourth industrial revolution is AI. It's the AI which makes the fourth industrial revolution a revolution. Otherwise, it's just third industrial revolution. So when you are adding AI to third industrial revolution, you get the fourth industrial revolution. And AI, as you would know, is something which is changing by the day, and things are happening faster than what you could ever believe. And AI certainly is going to affect every single thing which we do in our lives. So what I want to very quickly walk you through is to show you what can you expect and where we are and where we started from. So artificial intelligence has started more than 70 years back, 1950s, when it was initially conceived and the term was coined artificial intelligence. And this was put in dictionary as a capability of a machine to imitate intelligent human behavior. And of course, this is in a sense is still the definition of artificial intelligence. But as to how much imitation, how much intelligent human are we looking at is something which we keep discussing and debating. However, nothing really happened for the next maybe 20 odd years until 1970s and early 80s. It was primarily that it was a concept, not really any having any practical sense to it. And that's when the subsection, subfield of artificial intelligence known as machine learning came. And in machine learning, the machine started learning from the data rather than we requiring to program it. And that was a major shift in the way AI was being conceived. So now artificial intelligence was no more just a concept, but it was actually practically possible by making machines learn just by data. And that data became very important for this. However, it was soon realized that in spite of machine learning being able to learn from data, the learning performance becomes flat after a while. it tapers down. It asymptotically reaches a maxima. It cannot go beyond that, which means that no matter how much data you feed in, it will not improve beyond a certain limit. And this was a big limitation, because what it meant was that no matter what you do, your your machine will not be able to learn very advanced things. And human intelligence was much higher, and the machine's performance was much lower than the conventional machine learning, or the machine learning which we started in 1980s. Now that is where basically something very unique happened. And that is where in 1989 there was a celebrated research paper published. This paper was called Universal Approximation Theorem paper, UAT. Now, UAT was a paper which showed that there are certain set of algorithms, there are certain set of models which can learn almost anything in the universe, provided they are given enough data. So what it meant was that these models could essentially have no upper bound on their performance. They can perform to any degree of performance which you set, as long as you give it enough data. And this essentially meant that this curve which goes and it flattens, and there cannot be any more performance improvement in spite of you feeding more data, would be challenged and will be changed. And that is where the advent of universal approximation theorem created a new hope in the community. However, again, actually nothing really happened till early 2000, or maybe 2010 and onwards. And the reason was that people could not train this model. So you had a machine learning process where you had a model which could be trained on any data, and it could learn any data, but you could not train it. And that was a very big challenge, till that challenge was breached in 2010. In 2010 and thereafter, several researchers around the world were able to train the deep learning networks, the universal approximation models, which could learn everything and anything in the universe. And that is where this curve, which you see, the red curve, that came. And this curve is the curve for the universal approximation theorem, the universal approximators, the deep networks. And this, in principle, is a curve which goes till infinity. And thus, it means that you can feed more data to it, and its performance will keep increasing. There is nothing which it can stop. It will never have a upper bound to the performance. And this is a very, very powerful, I would say, statement, because you now are in a position to learn anything and everything in the universe which is existing. And it was so profound in a statement that people started calling it also a God theorem. So this kind of a theorem which can essentially says that you could have something which can learn everything, and probably only the God is the one who could learn everything. The only thing is, this is just next to God. It's not really God, because it is still an approximation, whereas God would learn everything precisely. So that is how this universal approximation theorem finally got practically used in 2010 onwards. And the reason why this was possible was because they started hacking a hardware known as a GPU. And this GPU hardware was what was the real reason why they could train these deep universal approximators. And that is where the next revolution of AI has started. And this is when we also call this the Cambrian explosion of AI, where the rate of evolution of AI suddenly increased by many, many fold. So this is something which is, I would say, a turning point in the history of artificial intelligence, because now with the advent of deep learning and the universal approximation theorem, your AI is able to learn everything. Now, this is very profound in a statement. Do you think this deep learning network will continue till infinity? Well, the theorem says yes, it will continue till infinity. So is there anything which can stop it? The answer is yes, it can be stopped by data. If you don't have enough data, this will not grow. So this only grows based on how much data you are giving. It also, of course, requires a lot of compute. So data is not enough. You need to also learn a lot of compute. You need to have a lot of computational power for the model to learn from it. And another very important thing is that if you have less data than this amount, if this is the amount, your data is less than this, then if the data is less than then this value, then deep learning networks, the universal approximators, are not the best method for performance. You can have a better performance by looking at conventional machine learning models. It's only that when they go beyond this, when the data goes beyond this critical value, do the conventional learning models perform poorer than the deep learning models, which essentially means that there are two takeaways. One is that the deep networks, the deep learning, the universal approximation theorem now opens up a window for us to learn anything and everything in the universe, provided we have enough data and computational power available. But at the same time, in cases where we have limited computational power, conventional machine learning algorithms will be better. Now, just to very quickly give you a sense of what all is possible by this. So, for instance, you look at the human ability to identify images or humans' ability to classify images. Now, if you look at that, you realize that this dotted line is the ability of humans as to how much error will they have when they are classifying an image. So this y-axis is the classification error, and the x-axis is, of course, the timeline. And what you realize is that in the beginning, in 2010, the error in classification by an AI was 28%. But then it started decreasing very drastically. And by the time you reach 2015, AI was able to do a better job than a human. And now we are, of course, on in 2025. So 10 more years till 2015. So we must have had AI which is even more powerful. So what happens is that humans do not have enough capability to classify images as AI has. And thus, in this specific case of image classification, AI is better than humans. Now, of course, the number of classes which humans know may be much, much more, and AI only has been trained, let's say, for 1,000 classes and things like that. But within those classes, it can identify things much better. Now, however, having said that, this is just image classification. Can AI do better than that? Because it's a universal approximation theorem which says almost everything is possible. So then, just to give you a sense of what all can deep learning and the universal approximation theorems do, is that they can learn from the image of your retina as to the age, gender, smoking status, and other things of an individual. Which means if you have a large amount of data, you can train the AI model on that data, and that will then provide AI model an ability to perform inferences and tell you what is the age of the person, what is the gender of a person, what is the smoking status of the person, is a smoker or a non-smoker, what is the diabetic state of the person, is the person having what is the systolic blood pressure of the person, what is the body mass index of that person. Now these are things which are not possible by a human to tell, but just AI looking at your retina can tell these things. Having said that, it can do more than just reading your eye. It can read your lips as well. And this is where, this is a video which shows that this can be, this lady, whatever she's speaking, is being looked at by these algorithms, and they can predict what she's speaking. Now this is again something very, very powerful, because humans really are not very good at lip reading, but we still know some people who can do lip reading. May not be as precise as this is. So this is certainly a very unique thing which is much better than humans. But it's still, I think we all will agree that this is not good enough. um, uh, so I hope my audio is still visible, because I'm showing an error, and I think it's um, am I audible to everyone?
Yes, sir. Audible.
Okay, I think so. That's fine. So I can't just get rid of this, but anyway. Uh, okay, good. So now so to for it to be more than just a lip reading or a retina reading thing, what about reading your brain itself? So what was found is that you can develop AI algorithms which can read your brain. And in this specific case, a person was put in an MRI, and the and the data from the MRI was used to decode what the person is looking at. So a person was presented with these images, and then the person was, the AI was asked to reconstruct those. So these were the images which the person looked at, and these are the images which AI reconstructed. And as you can see, this is not exactly one-to-one images, but it's very, very close images. These images are very close. And that basically means that your system can learn even to read your brain. And this is really scary that now it is probably closer to what we may think of as a God theorem, because it can actually read your mind in some sense. Now, what I showed you so far were cases where the the AI models, which were the universal approximation theorem based models, could perform inferences. They could infer what you are seeing, what you're saying, what your condition is, and things like that. But humans are more than just inferences. You can also create new things. So the question is, can AI create new things? And the answer is yes, actually, the AI can also create new things. And I just want to show you some images. So, for instance, what is common among all these people? What do you think is common among all these people? What is common among all these people is that none of these people exist. They're all AI created. So AI has created all these people, and this is basically something which you can create as well. Just go to let's say a website like thispersondoesnotexist.com, and you can create a new person from scratch, and which doesn't exist before. It can actually also create artificial intelligence can also create art like paintings, modern art, and an abstract art can be created. And that is again very unique, because this is something which is now no more of the domain of a human, and AI can do these things as well. It can also create music. So what you soon realize is that AI is not just able to do classification and regression and predictions, but can also be a creative power. And that's where humans now have to understand that AI is far more capable than just using it for predicting something or forecasting something. Taking it one step further, you could actually use AI and start creating maybe humans who could then become models. So this is an influencer, AI generated influencer, and this influencer is actually an AI generated influencer. She does not exist. So what happens is that this person is doing a specific work for various companies, but that company is making money, not that person, uh, because this person just does not exist. Similarly, this person, for instance, is, and I do not know, the video working? Okay, yeah. So this person again is a computer generated person. She doesn't exist. So what you soon realize is that computer can create some phenomenally unique, new things which don't really exist, and that becomes a challenge for humans to understand and accept. So there are a lot of things which AI can do, which humans can only think of. So I want to bring as to what impact does it make on our living society, apart from having these advertising agents on some of these videos being created. For instance, autonomous vehicle is one of the most I would say prominent thing which has been around. And for many years now, there are autonomous vehicles which are available, which run in the US and other places in the world. And these airports, by the way, you can just go to these airports and get an autonomous vehicle. You can rent an autonomous vehicle which will drive you around. So what you soon can realize is that you could be in an autonomous vehicle, where the autonomous vehicle is is basically taking you from airport to some other places. And these things exist where you are really not having requirement of any driver anymore, and a job of a driver is not needed. Well, job of a driver is one aspect. Can it also do more complex things? And the answer is, why not? So it can actually even do the job of a CEO, for instance. So this is a humanoid, which is the world's first AI CEO. Now, this humanoid actually is capable of doing everything what a regular CEO does, which is to look at all the various aspects of market trends, look at competitors, look at their own operations, look at new emerging markets, look at government policies, and then come up with the strategies to grow your business and maximize profit for your shareholders. And this Android is able to do all of those things. So then she becomes a very popular CEO because she's precise, she's perfect, she never, gets any data wrong. But above all, she never goes to sleep, never takes vacation, and never asks for a raise. And that becomes very, very unique because now imagine if she has to hire a new CFO or a CTO, whom will she hire? Will she hire a human or will she hire a humanoid? And that's a good question to look at. Anyway, giving you a sense of what AI is and where AI is going. So now coming back to our manufacturing. Okay, fine, great. AI has great stuff. So what does it mean to us in manufacturing? So for that, I want to quickly touch upon some aspects of manufacturing and the origin of all of this, which is from data. So what you realize is that data becomes the main currency when it comes to machine learning. And thus you need to be able to have data. And the data could be present in multiple different ways. It could be present in terms of large databases, tables, relational databases, but it can also be streaming, live streaming databases flowing from your shop floor, let's say. It could be data flowing, in from sensors. It could be data flowing in terms of, actual operations. And then it will also have a huge variety of the data. So the data could be in terms of sensor data, images, audio, temperature variations, text. So it could have a lot of different kinds of variety. And data also, of course, once it is so large, it will also be having some errors, uncertainties, missing data, and things like that, which is called veracity. So eventually, a data could be looked at as a combination. Big data can be looked at as a combination of these four aspects: volume, velocity, variety, and veracity. And these four things put together create a, a data, which then becomes your input for your data applications and machine learning. So now what I want to walk you through is that how is this data going to be used by us in industrial setting, in industrial AI? So I want to give you a very quick glimpse of what are the underlying algorithmic frameworks which are used for understanding this data. And in this, we are restricting ourselves not to all AI, but only machine learning aspects of AI. So in machine learning, we have models which we call as supervised learning models. These are the models where you have you have data input and output. There's something written on my screen. Do you think it is visible to all of you, or is it that black spot says it looks like you are sharing video? Is that visible to others also, or no?
Yes, sir, visible.
Because I want to get rid of that. I do not know how. I'm not able to get rid of that. Okay. Okay. Now it is gone away, I think. Okay, good. So, oops. Uh, I don't know. It seems to be back there. So I have more stuff on my screen and it gets hidden once that there's a black window on the top. Is that window also visible to everyone? Which says it looks acha, okay. Okay. So I'm not able to get rid of this. I don't know why. I'll just do something because that's hiding the text behind it. Give me a second. Let me just stop sharing for a quick second. And let's see if I can, if I can reshare my screen and not have um, that problem. So hopefully, okay. My screen is being shared now, I presume, right? Okay. And that is not there. So yeah, so these are the set of algorithms which we call as supervised learning models. these models are things which take an input data and an output data. So it's something where you have a input variables which control some kind of an output. So in your manufacturing setting, imagine these are your process parameters. You have the rate of heating, rolling, temperature of heat treatment, time for heat treatment, casting, overheat. So depending upon what manufacturing process you are doing, forging, forming, rolling, casting, welding, whatever you are doing, those process parameters become your input. And then your output could be aspects associated with quality, finish, productivity and things like that, which means you have a control over your input and that affects your output. So this is an input output relation which you have in your data. Now, these kinds of models are what are called supervised machine learning model, because they are being supervised to give a specific output. So you train them on input and output data, and then once you give it a new input, it will automatically give you an output. But in the beginning, you have trained it on an input and output data, and this could be of the kind classification or regression, depending upon if it is outputting a class or if it is outputting a continuous number, in which case it will be regression. Now, this is the regular kind of stuff which we have when we have an input and output data available. But very often we have data where we just have data, there is no output. There is no specific thing which we are looking at as an output. So how do we look at that? So now that is where you use unsupervised machine learning models, where you only have an input, but you don't have an output. You don't have a question to ask. In the supervised machine learning model, you had an input and you had an output, which was essentially a answer to a question which you were asking. But in case if you just have data but you have no questions, you still can use AI, you still can use machine learning, and in this case the machine will create answers to questions which you have not even asked. So this is very powerful, and this essentially brings a fact of human ignorance, which says that there are two kinds of ignorances which humans have. One kind of ignorance is the ignorance where you know what you don't know. So for instance, you are aware of that the general theory of relativity or string theory or quantum entanglement is something which you don't know, but you do know that you don't know these things. So this is ignorance of type 1, where you know what you don't know. But then there is another kind of ignorance, which is the most dangerous ignorance, which is the ignorance of you don't know what you don't know, which means you don't even know what you don't know. And thus you cannot go out and search for it. You can't go to web browser and search for something because you do not even know what to search for. You cannot go to an expert and ask a question because you do not know what questions to ask. Now, this is where the largest amount of ignorance is there with us, and we don't even know how much ignorant we are on that. So, what now happens is that the unsupervised machine learning models help us eradicate that kind of ignorance because they give us answers to questions which we have not even asked. And that is a very, very powerful, way of doing AI based stuff. So let me just very quickly walk you through, and then I'll come to examples. And I know I'm running short of time. It's already 10:40, and maybe I have 20 more minutes or so. So I want to quickly walk you through as to what all are the current things which AI can do very well or reasonably well, I would say. And I'm restricting myself to deep learning, the outcomes which are coming from the universal approximation theorem. So some of the things which AI can do quite nicely now is that it can do image classification, and that of course you saw before as well. It was able to do image classification. Uh, it can do image classification better than humans, and this is what is known as using convolutional neural networks, CNN based architecture of the deep networks. This is what we call as the inference image, where you can give it an image or a video and it can perform an inference from it. And example of this is AI driven automobiles is a culmination of all of this, where the AI is able to understand the surroundings and is then able to drive a car in it. The other thing which AI can very easily do is, for instance, it can do data entry, data cleanup, grammar correction. Now, these are some of the things which we have been using, let's say, Chat GPT for. These come as a part of recurrent neural networks and large language models. This can be further extended to general customer support, marketing, text article generation, small punchline writing, entry level programming, music creation. All of these things AI can do quite nicely now. And these are beyond just the inference. So these things were the inference AI, but now we have generative AI, Gen AI, which generates things. But this Gen AI can go beyond just music, code, and text. It can also create videos and images. So now it has come the full circle. It looks at an image and tells you what the image is, but then you can ask it that create an image of one kind and it will create an image. So it can now do both things. It can look at an image and tell you about it, or you could tell AI something and it will create an image for that. And these are a part of what we call as the latent diffusion kinds of models. These are generative AI models. Now, is that all what AI can do? Well, lately we have been pushing the boundaries of generative AI to the next level. We have been pushing the boundaries of generative AI to make it less hallucinative, make it more precise based on a context. And that is where domain specific insights and contextual search and question and answers started happening based on what we call as the retrieval augmented generation, which is RAG models. That's a part of a generative AI where AI is being constrained to give answers in a specific domain. Now, these are the things which AI can do quite well, and many of you must be using it. So let's see what it cannot do. So that's a bigger question, and this list is, by the way, shrinking every day. So today, AI models cannot solve complex multi-domain problems. Example of that is manufacturing problem. So just imagine you have a very complex manufacturing which you are performing, and AI will not understand all of that. So for instance, you have a welding operation happening. Your weld material, the base metal, the filler, the two base metals are different. The filler is different, temperature is different, the technique is different. You're doing one kind of welding over the other. So there is a heat transfer, there is a momentum transfer because melting is happening. There is a mass transfer and a diffusion, and there is a phase transformation, liquid, solid, solid, liquid. So there are lots of multi-physics stuff happening at different domain, in different domains and different length scales. And it becomes very tough for the current AI to be able to figure out what is happening. And that is because there is not enough data. Remember, AI can learn everything. So why can't it learn everything if it can't? Why can't it learn this? The very simple thing is that it can't learn this because we don't have enough data. So if we have a lot of data, there is no reason why AI cannot learn this either. But we have very narrow data. We also have hidden variables which we are not measuring. So for instance, you're not measuring the entry temperature and the exit temperature and the entire temperature of the furnace. You're just measuring temperature at one location, and thus you don't have many informations which are kind of hidden variables which you don't have. And then of course there are many other reasons why you cannot use AI for these multi physics problems. Now, having said that, it doesn't mean that you cannot actually. So AI is pushing and is trying to push, and that's when we have this architecture of agentic AI. And in this agentic AI is having multi roles. So there's a big AI, which is the X expert agentic generative AI, and that expert agentic AI has multiple sub agents which run mixture of experts models, and it goes through this whole thing using a chain of thought event. So this is where AI is heading today, and all the things which I showed you in the previous slide, which I said is not possible, are slowly becoming possible. Now this happens under a bigger gamut or a bigger umbrella of what we call as digital twins. So this is a concept where my private limited company, which I have inside IIT Bombay, works and creates digital twins for industrial manufacturing and other entire shop floors and entire plants. So what this does is that it is having a digital twin being created for something. And what a digital twin is what this shows. So a digital twin is a combination of a physical asset, which is the machine which you are trying to make a digital twin of, but also the surrounding and the human which is interacting with that machine. That physical data goes to the virtual 360-degree model of this using IoT, OPC, UA, MT connect, and various other protocols. And this virtual model then gives the data to the AI, and artificial intelligence looks at that data to create some understanding and predictions. However, if those information, if the data is not sufficient to make those predictions, then AI can ask analytical agents, AI agents, to do the same process. And thus, AI agents run some specific physics based simulations, let's say, and provide a physics based data to AI. So then AI has the real data and the simulation based data, and then it can make some observations. And then they are communicated to humans, to the World Wide Web, and to other machines. So this is a generalized concept of digital twin. So, so what this can be used for, let me just very quickly give you some examples. So this is an example in which we applied the expert generative AI to solve the problem of defects in a low pressure die casting situation. So this is a low pressure die casting manufacturing setup where there are 16 different cooling channels, and each of the cooling channel can be switched on and off for a specific duration. And the basic intent is the final wheel, the alloy wheel which is being cast, comes with no defects. Now 16 channels can be switched on and off at the time. What time you switch it on and what time you switch it off and how much pressure you provide to them are all variables. So you soon realize that you could have infinitely large number of variables because you could switch it on and off at any time. And thus, this becomes a very big problem which cannot be solved with the limited data which is available to us. This is the plots of various data on the right hand side, the pair plot of the data which was available. And that's why we get into a simulation. So this is where we are running computer simulations to generate where the defects are going to be most likely. And this data is then used to train the AI models, and then the AI models are able to identify when should you not be operating, when should be the most optimal window for you to operate, or what parameters you should have so that you have least defects. So this is one of the key case studies where generative AI with mixture of experts is used to determine what should be the final, what should be the final process parameters. Similarly, this is a application where we are looking at the cutting tool and the wearing of the cutting tool in a CNC machine. And here the data is coming from vibration, force, and acoustic emissions. And based on all of that, you train the machine, you train your AI model to be able to understand when the tool wear has become very big and you have a problem with the tool. Similarly, you could use this to identify problems with induction motors. And again, here we are having vibration data, current data, and acoustic data. And this is an actual example showing how this has happened. And this data is already published. So anyone who wants, they can probably have a look at it. This can also be used to look at machining quality, for instance, for chatter, for instance. So you can identify when chatter will happen, and AI can predict when the chatter is going to happen. But this can be taken to more complex systems also. So for instance, it can be used for predicting demand of a product. In this case, we are looking at the demand forecasting of jewelry. So we can predict when a jewelry will be needed and how much it would be needed and things like that. So this is a model prediction on the top, and the bottom is the actual sales which happened. And if you see the data is slightly, not exactly matching, but the day when we expect the maximum sale to happen, the prediction is actually when the day the maximum sale is happening in the actual values as well. The area under the curve for a day before and a day after put together gives you almost the same amount of sale, which is what you also see. So I can show you that demand forecasting, which is a very different area, also becomes a part of AI. It can also be used to predict, let's say, remaining useful life, RUL for a tire. And this is data where there is a truck which is being made to go around in this specific track, and we are measuring various things about temperature, pressure, and acceleration of the tire to predict how much is the remaining life of the tire. What I'm trying to give you a sense is that there are a lot of examples which I can come up with where we are using AI to make these predictions. So now what I will do is that I'll quickly switch to show you some of the live things which we have rather than just talk about in theory. And in the end, I would like it to be a little more interactive. So I would like to seriously hear from you all, and maybe if there are some possibility of taking questions, because I have a lot of slides. I can talk about it forever, but I don't want you to be, um, uh, not able to have questions with me. So what I'm doing is that I'm just walking. I'll just share my screen again, and I'm sharing the entire screen with you. Yes. So now what you're seeing, for instance, is the what you're seeing now, for instance, is the digital twin of a 5-axis CNC machine. And this 5-axis CNC machine is having its data go to the cloud. So right now we are having about 8,000 data points go to the cloud. And that data is then being continuously registered in the cloud for these AI techniques. So AI-based process monitoring, tool monitoring, spindle health monitoring, and chatter monitoring. So you can use that data to do this real time. And and just to show you, so right now the machine is working, where it's probably working very slow. It's basically, if you see, there is a speed, so it's working at this much RPM and at this much speed. And if you see, the machine is actually moving, and this is the real live as we speak right now. This is 10:59, on 2nd of September. Of course, the date may be a little off for that machine, maybe. And this, of course, is something which you can remotely work also if you like, but we don't want to. So what is now happening is that the data is going to the cloud, and the cloud is continuously monitoring it for those specific aspects. So now, if I may take you to the next thing which we have, let me just get rid of this. So this is a digital twin for a single machine. So now I can have a digital twin for an entire shop floor. So what I'm sharing with you is the digital twin for my lab, one of my labs. And I don't want you to think that that is how we make digital twin for all the factories. No, it will be different depending upon what they are. I cannot share with you any factory digital twins because those are proprietary stuff. But here I can show you my lab, and I can show you what we are tracking. So we are tracking temperature, humidity, and pressure inside each room. But then the key aspect is that we are tracking the health of each of my equipment. And in this case, if I start looking the health, so it says compressor health is green, and the vacuum system at the back, its health is green. There's a blinking green dot, and then the electron column is also blinking green dot, which means that the scanning electron microscope is also working fine. Now, how am I able to figure these things out? I'm having data from compressor, vacuum pump, and the electron microscope go to the cloud, and that data in the cloud is being looked at, and that is where I'm making that inferences. So for instance, if I give you, let's look at the data from a specific system, and I'm just opening one thing, and this is how the data from one of the electron microscopes is flowing. It is telling me beam is on, what is what, everything it is telling me, how the vacuum system has been behaving, how the ambient temperature has been behaving, relative humidity has been behaving, beam current, vacuum gun, and all those things are being looked at in one single window for you. But you don't really have to look at it because AI is continuously looking at it and is making those predictions. And this is the digital twin for this machine. Similarly, you could have a digital twin, which we have for all of these machines. And thus all these machines are having an AI based backend working, which is getting all of this information. I'll very quickly, get you some more examples. And after that, I would like to stop. Um, Maybe I'll just show you this one example. This is where we are tracking the movement of a truck and the tires it has. And in this case, we have multiple tires. So we have six, so we have two pairs at the back, so that's four, then again another four, that is eight, and plus four. So 12 tires are basically what are being looked at in this specific case. And what we are looking at is as to how the temperature, pressure, and acceleration of each tire is changing, how its RPM is changing as compared to its velocity, and based on that we can figure out how much is the wear which has happened in that tire. And then once we know that wear, we train it on it to predict what is the remaining useful life. If you see the latest temperature, the latest cold tire temperature is yellow. So what happens is that in this specific case, the tires have a temperature and pressure inside, and the temperature dictates the pressure. So if your pressure is X, so that would be different had it been a cold tire, because the temperature increase causes the pressure to change. So these are the actual pressures, these are the actual temperatures, and based on these pressures and temperatures, you can back calculate what would have been the cold tire pressure. So once you do that, you realize all these are okay, but this last one is under a very low cold, tire pressure, and that's not good for the case. So there are many, of course, more complex digital twin cases which are available, and I don't want to go through all of them, but I just wanted to give you a sense. I just wanted to give you a sense that you get an understanding of what is happening. So what I will do is now I'll just switch back to the last aspect of my presentation, and I want to quickly close by saying that, in summary, the AI and digital transformation is radically reshaping our world, and our world is changing extremely fast. The technology is changing so fast that there is no technology in the history of mankind which has grown so fast. And in all of this, the central role will be played by data. So data will play a very prominent role in all of this. Now, having said that, there are aspects where industrial AI cannot be solved just by industrial understanding, because the data is not enough. And that's where you would require engineering domain knowledge along with data. And that is how you create expert agentic AI. So an expert agentic AI is not a brute force method of training an AI, but a method where your engineering domain knowledge is used to create individual agents, and those agents are then given to a superior AI which uses all of them finally to provide you an answer. And that is the way we will be able to move forward. What will it do? It will be a disruptive change in our manufacturing. It will be a disruptive change in every aspect of our life. Jobs will become much cheaper. It will be able to perform manufacturing much better, higher productivity, higher quality, lower resource utilization, lower downtime. So there will be a huge impact which will happen. It certainly will have a more complex socio-economical impact. And I don't want to talk about that because it's a subject by itself. So with that, I will stop. I would be happy to hear from all of you. And if I can take few questions, I understand I have some 5-10 minutes still remaining. So this time I try to close quickly so that I don't just take away all the time. I want to basically also have some time for interactions. So I'll be happy to take some questions. I do not know how the moderators are planning to have the questions. People can
Thank
either
you, sir.
speak, or they could
Parts,
chat, they could participants could write maybe, or
yes, sir.
participants could speak.
Participant could write in the chat box for any query. Sir, we have a one query. How does the amount of the data affect the performance of deep learning network, and is there any saturation point?
So that's a good question. The simple answer is there is no saturation point in terms of deep learning. The whole idea about universal approximation theorem is that it can it can take as much data as you can create. The only aspect is that you may end up having not enough computational power to handle this data. Otherwise, there is no way to have a saturation. So there is no saturation. And how does the amount of data affect performance? Well, of course, you have more data, your performance improves. So if you look at models, there are chat gpt models which was 7 billion parameter models. Then you had 70 billion parameter models. Then now you're having 300 billion parameter models, and now you're going even bigger. And as the size of the model is increasing, that is because the the amount of data which you're using to train them is also increasing. So yeah, that's that.
Sir, we have another query, that is
Yeah.
the how do we avoid overfitting in supervised learning such as ANN models when training with limited data?
So this is something which is a very big problem, because if you have limited data, you end up overtraining. uh, and there are methodologies of avoiding overtraining, and it has to be done on a case to case basis. But the simplest thing is that you basically split your data into training set and a testing set, and then you train it on one, and then you see how does it perform on the data which it has not been trained on, the validation set or the testing set. And that gives you a understanding of how much of overfitting you're doing. There is always a compromise between the flexibility of the model and the overfitting. So what happens is, if you make a model very flexible, it does overfitting. And if you make it very rigid, then it is basically not really having a good variance. It has very high variance then. So what happens is that if you look at in general the supervised learning methodology, there are two kinds of errors which come in. One is the bias which the model has, and the other is the variance which the fitting causes. And both these get added up, and it's a play between variance and bias. So for a limited data, you cannot reduce both variance and bias. As the data amount increases, you actually have the ability to reduce variance and bias, and thus you can achieve a better fit. But with limited data, it's always a challenge. So the data is certainly the most important aspect. So let me see. So I can read now. In current scenario, computational power is used by individual manufacturing units or by cloud. What's the future? So it all depends upon how much of data secrecy you want. If you want your data not very secretly, you can certainly ask cloud. Cloud is much cheaper. And you could have, of course, your secrecy built in there as well. You could have your data encrypted. You could have your own, you know, um, I would say individual servers which are protected. So there is a data protection possible in the cloud as well. But in general, when the data is in the cloud, it is out there for someone to hack. But if the data is within your system, if it stays on premise, then you certainly cannot lose the data. So that is one of the reasons why you may want to look at cloud or on premise based on cost. Cost is cheaper on the cloud, more on premise, but data security has lesser issues on premise, but it has a bigger issues on cloud. Another reason which can dictate a difference between cloud and on-prem application is that if you have very large amount of data, if you have a very large amount of data, then the bandwidth of sending the data to the cloud becomes limited. This happens, for instance, in our vision system. So we do very advanced visionetics based systems, where we have advanced AI based vision systems, where we are taking video cameras from, let's say, 500 different video streams. Now I cannot send all of these 500 to the cloud, because the bandwidth required for high resolution video streaming of 500 would be very large. And that's where I may want to do an on premise based thing. So it depends upon your specific requirement, your needs, and the data requirement. Any other question?
Yes, sir, we have one question basis that what are the basic infrastructure or basic setup that we needed to apply AI ML in metal additive manufacturing for any defect detection?
So that's a very good question. I didn't talk about what I do apart from what you had presented. I will probably just take 2 slides to show metal additive manufacturing. So we have one of the largest additive manufacturing facility in India in my lab here. We do a lot of metal 3D printing, and I just want to quickly show you uh, the facilities which we have and what we do. So I'll just probably share one um, small slides and then maybe answer this question, because I realized that I should have probably been more um, yeah. So you can see my slide, I hope now. And this is my digital manufacturing research setup. So I do a lot of different applied manufacturing research with AI, and they are in all possible domains. So I do very advanced additive manufacturing. I do additive and subtractive. So that DMG machine which I showed you is one of the machines which I have, but I have very large Haas machines for doing metal 3D printing. This part which you see has been 3D printed. I also do composites. I do research in and manufacturing of composites. I do machining, casting, limited casting. So I'll just maybe show you. So this is my facility, the additive manufacturing facility. Uh, and then again, I have a digital twin for this entire manufacturing facility. Then I also have advanced characterization facilities where I have electron microscopes and everything, and I showed you a small digital twin of that. I also have one of the most advanced 3D X-ray uh, tomography facilities. So one of the most advanced 3D tomography facilities, multiple field emission gun electron microscopes, dual beam gallium ion microscopes, 3D microscopes, X-ray diffractions. I also have advanced machining facility. So probably again, one of the most advanced facilities in Indian universities. I have this DMG DMU 75 mono block. It's a highly optimized machine created for aerospace applications. It can take large torques and large RPMs. Again, it is fully digitized. We have the data flowing from this to the cloud, and we create digital twins. I showed you that. Then I also have composites manufacturing facility where we do not just simulations, but we manufacture composites using autoclave 3D printing and VARTM. And then we also do post processing and characterization. And again, we have data from this flow. Then we also have a very advanced group on IoT. And these are some of the IoT devices which we displayed in one of the industries. We have IoT devices from almost anywhere to anywhere, any physical parameter which can exist, we can detect it. So we can detect vibrations, current waveform, voltage waveform, magnetic stray field, ultrasonic emissions, sound emissions, RF spectrum, waterfall, you name it, we can measure everything. And then, of course, I have all of this data flow in into an applied AI industry 4.0 research group. And and what happens is that this is something where finally all the understanding of AI, IoT, and manufacturing comes together. So this is what I do now. What is the infrastructure required for this? Well, it depends upon what you are doing. So the infrastructure, of course, for an additive will be that you will need an additive machine. But depending upon what kind of AI automation and AI based industrial AI based you know want to have for your additive facility. So you could start with one GPU based systems, maybe a 4090 RTX kind of a system would be sufficient, which would be not very expensive. Within 5 lakhs or so, you should be able to get a decent enough system where you could run most of these AI systems. But if you really want to go for bigger things, then it can really balloon up. It could have a very large amount of costing. Yeah.
Thank you, sir. So we have another query in the chat box.
Right, yeah.
What are the available postdoctoral fellowship opportunities in at IIT Bombay, and what eligibility criteria application process for PhD graduates?
So it's a very case to case basis. One can go online, look at what is the PhD, criteria. So every institute has a very elaborate process. So you can just visit IIT Bombay. Me saying something here which is not exact may lead to a wrong understanding. So I would refer you all to IIT Bombay website. We have one of the most advanced, I would say, PhD program, and we'll be happy to entertain all great bright students, coming from your good institution, from your great institution.
Thank you, sir. Thanks a lot uh, for your
All right.
for your very insightful concept in digitalization and automation in manufacturing processes, including real-time example to make it more understandable. So we look forward for the future collaboration, sir. Thank you, sir. Thanks a lot once again from all side.
Thank you.
Thank you, sir.
All right. Bye bye.
Bye. Participant B will join the next session after the short tea break at 11:30.